Okay, guys, so now an introduction to ICMP version 6 from RFC 4443. And also we're going to discuss a little bit about the IPv6 Neighbor Discovery Protocol, which actually is also part of ICMP version 6. So as you can see here, ICMP version 6 is actually its own IP protocol 58, and this is the general format. So basically, we'll have on our first 32 bits the type that indicates the format of the remaining IPv6 message. We're going to see some examples of different types. Then we have the code, which depending on the type is going to have more information and message granularity, for more options and things on that specific message. And as usual, checksum, right, to make sure that the packet arrived correctly. So as I was saying, here are some examples of ICMP type messages. Basically on RFC 4443, those two types of messages are defined, error messages and informational messages. You may find this familiar from IPv4, where we have also destination unreachable, packet too big, in this case when it exceeds the MTU, time exceeded, if you remember the hop count for maximum hop count for a message, and parameter problem, this is when for whatever reason it is a correct IPv6 message, but some of the information or the code is incorrectly created. So the packet is discarded, and the receiver sends a parameter problem saying, send this again, you format the packet incorrectly. And finally, IPv6 informational messages. We're also very used to this in IPv4 as echo request and echo reply, the typical ping test. Okay, guys, let's keep going. Now we're going to discuss a little bit about ICMP version 6 and also about the Neighbor Discovery Protocol, which is also part of ICMP version 6. In this case, we start with RFC 4443, which basically defines the general formats of ICMP version 6. Particularly, we have here IP protocol 58. It has its own IP protocol, and the general packet is going to be always like this. It's going to have a type, a code, and a checksum. In the case of the type, it's going to say what kind of a message we are sending or receiving. In the case of the code, it's going to depend on the type of the message, and it's going to provide more information for that packet. And the checksum, as usual, to make sure that there's the data arrived correctly. Here we have some message types for RFC 4443. It defines basically two major categories. One is error messages, and the other one is informational messages. This is very familiar for everybody, as it's very similar to IPv4. So we have error messages as destination unreachable, packet too big when it exceeds the MTU. We have time exceeded when we exceed the hop count for the packet, and parameter problem. This is when the receiver actually receives like a kind of a valid IPv6 ICMP packet, but maybe the code or information within the packet is not correctly placed. So it's going to discard the message and send back a parameter problem saying you have to redo this packet and send that again. And informational messages, we are all familiar with this one, is our dear ping, echo request, and echo reply messages. And here you'll see, if you want to go to the RFC and check a little bit more, these are all the sections where you'll find specific packet format and all the characteristics and parts of the packet for each of them. Then we go a little bit deeper into Neighbor Discovery Protocol. This is defined on RFC 2461. So this is quite important for IPv6, and much of the under the hood functions are let's say are placed by the Neighbor Discovery Protocol. So I put here words are, right? Remember that in IPv6 we no longer use broadcast. So ARP is a broadcast protocol for IPv4, so we no longer have the ARP protocol. So how we know which is the MAC address of my neighbor, either it could be another host or my router. How do I get the layer 2 address? Well, this is one of the functions of the Neighbor Discovery Protocol. So here, as we can see here, one of the functions is to get or determine the link layer address of my neighbors. And it is also used to understand which routers are on my local link. We're going to see this also a little bit in a few more slides. And as we were saying, specifically, Neighbor Discovery defines 5 more ICMPv6 types, which are 133 and 134 for router solicitation and router advertisement, 135 and 136 for neighbor solicitation and neighbor advertisement, and 137 for redirect, right? Going a little bit more deeper here. So router solicitation and router advertisement, this is going to be when the host wants to know which are the prefixes that it can use for auto configuration. We're going to see that also later on and in the lab. And our advertisement is actually the router saying, yes, all these prefixes are available for you to use on this link. Neighbor solicitation and neighbor advertisement, this is basically what ARP has become. So basically, when a node needs to know which is the link layer or the layer 2 address of another host, it's going to send a neighbor solicitation, and the neighbor advertisement is going to be the reply for that message. And finally, the redirect is going to be sent if you have more than one router in the same link. Those messages can be sent to make routing more efficient. Okay, so we're going to discuss now more about neighbor discovery job description. This is kind of what the protocol is intended to do. This is all well written in RFC 2461, but basically all these functions are performed by neighbor discovery protocol. So as we were saying, router prefix and parameters discovery. So the hosts, when they come up, the interfaces on the links, they're going to know if there are routers on the links, and if there are routers, which prefixes are on the link and can be used for auto configuration. For address auto configuration and resolution, so I'm gonna use the neighbor discovery messages for again, to learning those prefixes, and my interface is going to be able to use those prefixes for auto configuration. We're going to see a little bit later how. And resolution also, as we were saying, to get layer 2 addresses from my neighbors, and also to keep that table updated, right? If for whatever reason the layer 2 address changes, my neighbor discovery protocol is going to help me update that my cache table. Next, hop determination for routing, and neighbor unreachability and duplicate address detection. This is also when the interface comes up and it says, okay, I'm going to use this IP address. It's going to make sure first that there's nobody else using that IP address. So it's going to use this DAD, which is duplicate address detection, and redirect, as we already discussed. Okay, 2 more slides before we go to our demo lab. So first of all, I want you to remember these important multicast addresses. They are very related to neighbor discovery and all that happens in the link local environment. So first of all, FF02:1 all nodes. Remember, when we say nodes in IPv6, we're speaking about both routers and hosts within that link. Then just routers is going to be FF02:2. And particularly when we say a solicitation message to get the layer 2 address, we're going to use this solicited node multicast IP address, which is always going to be built using this prefix here, FF02:1FF, and then the last part of the IPv6 address, as you see here in the example. So this is not only to get the layer 2 address of a particular neighbor, but also it's going to be used for DAD, duplicate address detection, saying, okay, if I don't receive any reply from this address, that means that address is not being used. And finally, just we're going to present a little bit about the lab and some specific things for auto configuration. So if you remember, for IPv4, we just basically have two ways to configure our hosts, either DHCP or manually setting all the IP settings like IP address, subnet mask, default gateway, etc. But for IPv6, we have like three flavors. One is that, let's say, completely automated, which is the Slack, stateless address auto configuration. In this case, if you remember, getting the router advertisements, the interface is going to be able to use that prefix and build its own address. Remember that we also have the link local address that's also automatic, just using the link local prefix and the MAC address using the UI 64. You can see how that is built also in the RFC. And then we can have the stateful DHCP version 6, which is kind of like our old, very similar to our old IPv4 DHCP service. And then we have kind of a solution in the middle, which is a stateless DHCP version 6, where we're going to use the router advertisements to get our prefixes, but we're going to use also the DHCP server to get some other parameters like DNS, for instance, or domain, right? And in the lab, we're going to use that option. And finally, just to present the lab here, we're going to use this unique local addressing. Not sure if you remember, but in IPv4, we have our RFC 1918 addressing, which is a private addressing. For IPv6, it is defined as unique locals. And we have, here you can see the link. The idea is that you generate this prefix for you, this /48, and the idea is that anybody that needs to use private IP addressing use auto-generated unique local prefix, and the idea is that it's very, very unlikely that more than two sites are going to have the same prefix, right? So if you read the RFC, the probability that of clashing of the prefix is very, very, very small. So I've used this page. Check it out, and we're going to use this addressing here. So real quick, our lab is going to consist of an IPv6 host, LAN switch. We're going to use VLAN 2000 to connect this host over here. This is going to be our default gateway, our IPv6 default gateway for this VLAN segment. And we're going to simulate a WAN here, just it's this single router, and the DHCP version 6 server. This is also going to be a router with the DHCP version 6 servers configured. And this is the address of the server. Okay, see you in the lab demo.